In geometry, you learned formulas that show how a circle's radius, circumference, and area are all related to each other. In this lesson, we are going to talk about how circles can be represented on the Cartesian plane. Let's begin this lesson on circles with a little recap on triangles. Trust me, you'll see why. We know that right triangles have the special property that the lengths of their sides can be related with the famous Pythagorean theorem, a squared plus b squared equals c squared, where c is the length of the hypotenuse. For example, this equation tells us that a right triangle with sides a and b equal to 3 and 4 must have a hypotenuse of length 5 because 3 squared plus 4 squared equals 9 plus 16, or 25, which is also 5 squared. While keeping this Pythagorean relationship in mind, let's now take a look at a circle on the plane. This circle has a radius of 5 and is centered at the origin. Let's begin to think of how we can write an equation to represent this circle. Because the circle fails the vertical line test, it is not a function. So we can't write an equation in the form y equals something like with a regular function. Instead, let's think of this circle as a collection of points, each of which is exactly 5 units away from the origin. How can we think of the x and y coordinates of all these points? One way to do so is to draw the horizontal and vertical components of the radius line coming from the center of the circle. We can see that this point on the circle is horizontally 4 units away from the center and vertically 3 units away. Now you might see why we started out talking about triangles. Now that we can see the radius connecting to one of the points and observe the x and y components separating that point from the center, we can understand that each point on the circle corresponds to an unseen triangle. These triangles will help us represent the circle as an equation. We are going to use the Pythagorean theorem, but instead of using a, b, and c, we're going to use x, y, and r. This will give us x squared plus y squared equals r squared. This circle, as we said, has a radius of 5, so we can plug that in for r. So we'll have x squared plus y squared equals 5 squared. And of course, 5 squared is 25, so it becomes x squared plus y squared equals 25. And this is actually all that we need. We now have an equation which represents this circle on the Cartesian plane. In fact, we can easily represent any circle that's centered at the origin using x squared plus y squared equals r squared as a template. A circle with radius 2 would be x squared plus y squared equals 4, and a circle with radius 10 would be x squared plus y squared equals 100. Of course, not all circles are centered at the origin. Let's take a look at one such circle now. This circle is centered at the point 2, 1, and has a radius of 2. On the previous circle, we found a way of representing all the points on the circle by relating the radius to each point's horizontal and vertical distance from the center. With this circle, we are going to do the same thing. This time, the point xy on the circle is x minus 2 units away from the center horizontally and y minus 1 units away from the center vertically. Pause the video here if you need a moment to convince yourself. Earlier, when we observed the circle centered at the origin, the horizontal distance of a point on the circle from the center was x. The vertical distance was y, and the equation of the circle came out to x squared plus y squared equals r squared. Now with the circle centered at 2, 1, we are going to modify that equation by changing x to x minus 2 and changing y to y minus 1. This gives us x minus 2 squared plus y minus 1 squared equals r squared. And since we know that the radius is equal to 2, we then have x minus 2 squared plus y minus 1 squared equals 4. And this is the final equation of the circle. More generally, we can write the equation of a circle centered at the point hk as x minus h squared plus y minus k squared equals r squared. By subtracting h from x and k from y, we offset the fact that the circle's center is moved away from the origin by h units horizontally and k units vertically. This format of writing the equation of a circle is aptly named center-radius form. Of course, a circle centered at the origin still follows this hk form as well, just that h and k are both set to 0, and we simplify to x squared plus y squared equals r squared. Let's now discuss a second format for writing equations of circles, the general form. The general form of an equation of a circle is an expanded version of center-radius form, with the terms written in a specific order. That order has the x squared term first, followed by the y squared term, then the x term, the y term, and finally the constant. On the right-hand side of the equation is a 0. We can represent the general form in this way, where a, b, c, d, and e are all constants. Ax squared plus by squared plus cx plus dy plus e equals 0. Despite its name, the general form is actually less popular than the center radius form, but we can always convert a circle's equation from one form to another. In fact, let's try that now. Using our equation for the circle centered at 2, 1 from earlier, let's expand and simplify to convert it from center radius form to general form. So our center radius form equation was x minus 2 squared plus y minus 1 squared equals 4. Our first steps will be expanding the x minus 2 squared and the y minus 1 squared. So if we expand x minus 2 squared, we'll get x squared minus 4x plus 4. And if we expand y minus 1 squared, we'll get y squared minus 2y plus 1. And this is all equal to 4. So now, on the left side, we can combine our constants, 4 and 1, and we'll get x squared minus 4x plus y squared minus 2y plus 5 equals 4. And then, since we want the right-hand side to be a 0, we subtract 4 from both sides. So we'll have x squared minus 4x plus y squared minus 2y plus 1 equals 0. The only thing left to do now is to order the variable terms correctly. Remember, the x squared term is first, then the y squared term, the x term, the y term, and finally the constant term. So this will give us x squared plus y squared minus 4x minus 2y plus 1 equals 0. Our circle's equation is now written in general form. While this equation looks much different, it still represents the same set of points which compose the circle of radius 2 centered at the point 2, 1. Let's now try converting an equation in general form to center radius form using the circle 2x squared plus 2y squared plus 8x minus 16y plus 22 equals 0. To get us started, let's group the x terms together and the y terms together. So we're going to have 2x squared plus 8x plus 2y squared minus 16y plus 22 equals 0. Next, we are going to complete the square. There are 5 steps for us to follow here. First, we need to move the constant term to the right-hand side. This will keep it out of the way for the following steps. So we'll have 2x squared plus 8x plus 2y squared minus 16y equals negative 22. The second step is dividing all terms on both sides by the leading coefficient. Here that leading coefficient is 2, so we're going to divide all terms by 2. So that will give us x squared plus 4x plus y squared minus 8y equals negative 11. Of course, sometimes the leading coefficient will already be a 1. In this case, dividing all terms by 1 produces no change, and this step may be skipped. The third step is grouping all the x terms and y terms together with parentheses, leaving room for a third term in each group. So we'll have x squared plus 4x, and then leave room for a third term, plus y squared minus 8y, and again leave room for a third term, equals negative 11. This space is important for step 4, which is to take the coefficients of x and y respectively, divide them by 2, and square them. These resulting numbers are added to both the left and the right side of the equation. So for the space following 4x, we're going to take half of 4, which is 2, and square it, which gives us 4. So we're going to write a plus 4 right here, and we also need to write a plus 4 on the right side to keep the equation balanced. For the second space, we will take half of negative 8, which is negative 4, and square it, giving us positive 16. So we're going to write plus 16 right here, and again, we're going to write it on the right side as well. The fifth and final step of this process is factoring the left side, which contains perfect squares, and simplifying the right side. In the first set of parentheses, we collect the square root of x squared, the sine of the middle term, and the square root of 4 to get x plus 2 squared. From the second set of parentheses, we collect the square root of y squared, the sine of the middle term, and the square root of 16 to get plus y minus 4 squared. And then on the right side, negative 11 plus 4 plus 16 gives us positive 9. Our final result is the equation of the circle in center radius form. We can now see that this is a circle with a radius of 3 centered at the point negative 2, 4. We've learned that circles can be expressed using equations in center radius form and in general form. Converting from center radius form to general form requires some expanding and simplifying. We can also convert equations of circles from general form to center radius form by completing the square. While completing the square involves many steps, as always, you'll have it mastered with a bit of practice. I hope this video has been helpful. Thanks for watching and happy studying.